Okay, so this will be the first in a series of videos here for lesson 12, where we're going to talk about putting all of these strategies together, right? Probably the most difficult thing in probability is deciding which strategy to use, because sometimes multiple strategies work, maybe one is more difficult than the other, right? So this will be the first in a series, and generally the problems are going to get more and more difficult. This first video will cover problems that you could see in any of the math classes that we teach in high school or early college. To start with, though, why is it that probability is so challenging, right? When you start doing probability, it seems like every problem requires a different strategy, right? And we've looked at in the previous video lessons a whole lot of different strategies. And yet your teacher seems to just kind of know what strategy will work for each problem. It can be really frustrating when you're first starting out learning probability, right? But there's a reason why your teacher knows what strategy to use for every problem, and that's because they've done hundreds of probability problems, so they can actually see the patterns, right? They can see that there's a whole class of problems that use one strategy and a whole class of problems that use another strategy and so on. And so with their big picture view, they can kind of see the patterns that are involved, right? So the goal is to try to expose you to enough different problems so that you can start to see those patterns. And then hopefully in this video, I'm going to try to put together some ideas to help you see those patterns and maybe help you with a kind of a procedure to help you select what strategy or strategies to consider. So if you go to my website, which is at www.mrfelling.com /library, there is there's a link to all of these different videos in the series. So if you came to here through YouTube, there's actually a page on that website that has links to all the videos that kind of shows their organization. And for this lesson 12 video, I have a PDF of this document. This is the best I've been able to come up with so far as a way to kind of list all the strategies and show their organization. So basically there's kind of two classes of strategies, and they're used for different situations. So the big difference is some problems are discrete problems and some problems are continuous problems. And that means that the variables we're considering are the quantities. They're either discrete values, like say, if we're talking about a raffle, like values of you could win $0 or $10 or $50, or they're problems that involve counting, where the problems can be, the solutions can be integers, like you could have one of something or two of something or three of something. And there's a whole series of strategies related just to that. And then there are separate strategies over here for continuous problems, where we're talking about like finding an average value, right, with maybe the lengths of fish or something, where there's a whole infinite range of values. And then once we've decided whether we have a discrete or continuous problem, right, we also have to say, are we talking about actually computing a probability, right, or are we finding something like an expected value or an average value? Because there's different strategies for those, right? And then depending on the probability problem, say for discrete, we might ask, are we talking about a single event or multiple events? So what this is trying to do is to kind of list out the probability strategies that we've looked at through lessons 1 through well, really 2 through 11. And what's indicated in these little parentheses, these numbers, are the lesson number that covers that strategy. So we're gonna look at this document and use it as a way to kind of help see what strategy we should use, right? And then, yeah, so this is my website here, www.mrfelling.com. If you put /library, there should be a link to the to this page that shows all the lessons. And then to lesson 12, there's an item here that links to the lessons themselves. There's probably more than one video here, right? But then we've got the strategy tree that I just showed you, and I also have a PDF document that lists kind of a summary, just with a piece of paper, of the different things to know about each of the strategies. Okay, so you can refer to those documents as kind of assistance, things that can assist you when you're investigating a problem. Okay, so we're going to talk about the first problem here. We'll go through a series of problems and we'll stop and we'll pick up in another video as we get to harder problems. The first one, I'm actually going to solve this problem 3 completely different ways. And I'm going to actually state the same problem using different ways to state the information. And we're going to find that certain strategies work better depending on how the information is listed. So here's the problem. It says a random sample of 100 students were asked whether they preferred regular or diet soda, with the results shown in this table. So we tracked how many people liked regular and diet, and we also tracked their gender, whether they were female or male. And those were the numbers that were given. So we're going to be asked to find probabilities that what's the probability that a randomly selected student would prefer diet soda? What's the probability that a randomly selected student would be female? What's the probability that a male student would prefer diet soda? What's the probability that a student who prefers diet soda would be male? And what's the probability that a randomly selected would be female and prefer diet soda? Okay, so pause the video, try this, and then unpause. Okay, so as I'm thinking about this, I'm looking at my chart here of possible strategies, and the first thing is I notice that the numbers involved here, these values here, are all integers, right? So we're talking about a discrete situation here, right? So that means we're only going to consider strategies that are used for discrete probability. We are talking about probabilities, so we're talking about a probability problem here. And then what about the events? Well, if I look at this, it says find the probability that a student is selected that meets some criteria. So we're talking about selecting a single student. I think that means we're in the single event case here. We're not talking about multiple events and combining an and or and things like that. And so really, there's only two things it could be. It can be a conditional probability or a simple probability. So simple probability is where we just take out of the entire total some number that meets the event. So it's the count in the event sample space, or event divided by the count in the sample space. And for conditional probability, we think about creating a conditional sample space and an event out of that, right? So, so all of these are either simple or conditional probabilities, and we're going to use the strategies available, right? So we've got things here like count up things, right? We can use equally likely cases, counting the event space, things like that. Okay, so if I were to look at kind of what I know about conditional probability, because some of these are that, I would remember that when you're finding a conditional probability, you write the probability statement this way, where you're finding the probability of something given that you have an event, like maybe the probability that somebody likes playing video games given that they're a girl. Right? And the other thing that's important is that when you have a conditional statement like that, the denominator of the fraction that we're going to form is always some sort of counter probability related to the condition, and then the event is the numerator, and so it's out of that conditional sample space. Right, so this is just kind of a summary of ideas. All right, let's take these each at a time, and I'm going to go ahead and actually I'm going to get rid of this thing right here. So it's out of the way. Let me get rid of that. And we've got this table. So the first thing we should do is we should go ahead and add up all the rows and columns. So we ended up having a total of 60 females and 40 males. There was a total of 34 regular drinkers and 66 diet drinkers for a total of 100. So if you're given a table, then we're just going to use the table directly as much as possible. Okay, so for part A, it says to find the probability that a student prefers diet soda. So if I were to write the probability statement, I'm just saying what's the probability that a student likes diet. Okay, so that's a simple probability, which means the denominator is going to be the entire sample space, all 100 students here, the entire sample space. And then I just need to figure out what's the total number of people that like diet, and that would be the 66 number, the marginal value there. So 66 out of 100, that probability would be 0.66. Okay, so that one's pretty straightforward. In fact, I can kind of show on the table what I'm doing here. I'll do that as we go. So what I'm saying here is we're talking about the entire table, right? In fact, let me, so that I can erase and use this, I'm talking about the sample space is the entire selection of students, and then I'm talking specifically in the event about including the ones that are in the diet. So out of the 100 students total, 66 of them were diet, and that's how we came up with this fraction right here. Okay, let's look at number B. This one says to find the probability that a randomly selected student would be female. So the probability that a student is female, we could write like that. And so that means that this is a simple probability, right? And so that means that, again, the sample space is going to be all 100 students, right? All 100 students there. So the bottom of this fraction would be 100. And then the top of the fraction, the numerator, is going to be the event that they are female, right? So that is going to be just the sum of all the female students, which would be 18 plus 42, which turns out to be 60, right? So I can even write it like that. 18 plus 42, it's 60 out of 100, or 0.60. So a 60% probability that a randomly selected student here would be a female. Okay, for part C, it said find the probability that a male student would prefer diet soda. So a male student is really a condition. We're really finding the probability that somebody prefers diet soda. We're finding the probability that somebody prefers diet soda given that we know that they're male. Okay, so this is now not a simple probability. This is a conditional probability. And that means that the sample, we're not going to use the entire table. We're going to use only the portion that meets male. And so we're going to restrict ourselves to a conditional sample space of only the 16 plus 24 students that are males, right? There were a total of 40 males. So out of those 40 males. Now, the event will be that they like diet soda, right? So that's going to be staying within the conditional sample space. The ones that like diet soda are the 24 there. Right, so that's going to be 24 out of that 40, and 24 out of 40 is also 60%. That's a coincidence that it happens to match the other number there. All right, so a conditional sample space because we have a conditional probability. Okay, for part D here, it says find the probability that a student who prefers diet soda would be male. So again, student who prefers diet soda. The who prefers diet soda part is really the condition. You could remove it and the sentence still makes sense. Find the probability that a student would be male. That's what we're finding. The probability that a student is male, given that they like diet soda. So this is the reverse condition here, right? We're talking about that. And in that case, that means that the sample space, the conditional sample space is going to be the diet soda drinkers. So we're restricting ourselves to this column here. And then we're saying, okay, so the bottom of the fraction will be the 42 plus 24, which turns out to be 66. And then out of that, we want to know the number of people in that conditional sample space that are male. So that would be 24 here, right? So 24 out of 66, 24 out of 66 turns out to be 0.3636. All right, so about a 36% chance for that probability. All right, and then the last one says here for E that we want the probability that a randomly selected would be female and prefer diet soda. So female and diet soda. Female and diet. I could write it like that. Now that really is a compound probability, but we could, with a table, analyze that as a single probability like this, because if there's no line here, it's not given a condition, so this is still a simple probability, meaning out of all of the students, all the 100 students in the table, we're wanting to know how many of those are female and diet soda, right? So that means they have to meet both conditions. They have to be female in the female row and the diet column. That would be that 42, right? So this would be 42 out of 100, or 0.42. So that would be the probability. Okay, so this is how you would solve the problem if you're given a table. If you're given a table, you can do a lot of calculations of simple probabilities and conditional probabilities just directly by looking at portions of the table. Okay, so another way that we could have been given this exact same information, so we're going to get these same answers, we might have been given information in another way besides as a table. So this is actually the same problem, but it might be stated this way. A sample of 100 students, 60 female and 40 male, were asked whether they prefer diet or regular soda. 70% of the females preferred diet soda, and 60% of the males preferred diet soda. And then we're going to ask the same question. Okay, so pause this and see if you can come up with a different strategy to use that information instead of a table. Try to avoid using a table this time. Okay, so to me, once I have percentages, right, especially percentages for conditions like 70% of the females, 60% of the males, that implies that I can kind of list the two cases, gender and their preference, as kind of two events. So let's explore using a tree to represent this situation. Okay, so I'm going to do this kind of over and over again. The first one, let's make a tree for part A. And what I'm going to do is say, well, the person could be a male or a female. And the probability of that, well, we were told the counts here, that there were 60. So 60 out of 100 students are female, and 40 out of 100 students are male, right? And then if I know that I'm a female, then 70% of the females prefer diet soda. So I could say 0.70 is the probability of preferring diet, and preferring regular, therefore, would be the other 30%, right? And same thing down here. Yeah, so if I had males, they could prefer diet, or they could prefer regular. And in this case, it said 60% of the males prefer diet, and that means 40% would prefer regular. So one way, if you're given percentages to display the information, would be to construct a tree diagram like this. Like since this is 70% of the females, it implies that the female choice would have to be made first. So the gender choice is made first. Okay, so let's see if we can use this to answer the question. We want the probability that a randomly selected student would be female. Okay, so well, that is just a certain portion of this tree, right? It's just this right here. It's taking this branch and stopping right here. So it would simply be this first probability, right? The 60%. In fact, I could just directly say that that probability is 60 out of 100, right? Wait a second. I did the wrong one. It should be diet. Let me back up for a second here. Wrong question. I was answering B. Okay, so we had 60, 40. So this is the probability that a student prefers diet soda, right? Diet soda. Okay. So that means that's more complicated, because where is diet soda on this tree? Well, you can have diet soda this way, or you could have diet soda this way, okay? So I want to explore this a little further. I'm going to move this over. We want to find the probability of diet, okay? All right. So first of all, to get to diet here, right, you'd have to be female and like diet soda, right? So just taking this one probability right here, this probability right here, how would we compute that? I'm going to remind ourselves that we have and or rules, right? So and is multiply. So what I'm really saying is this green check mark here is the probability of female and diet. And on a tree, you could think of it as being the probability of female and then times the probability of diet given that you were a female, right? So it's going to be this first probability of being a female is 60 out of 100, and then the probability of liking diet given that you're a female is the 70%, right? So, and since it's and, we would multiply. So this probability out here is 60 out of 100 times 0.7. We would multiply as we move across the tree. Okay, and that's one of the ways to like diet. The other way is the second check mark, and for similar reasons, this would be the probability of being a male, which is 40 out of 100, times the probability that you like diet if you are a male, which is 60%. Okay, but here's the thing. Now I've got this way to like diet, or I could also like diet this way, and we know in general that the formula for, let's say we call this event A and this event B, the probability of A or B happening is the probability of A happening plus the probability of B happening minus any intersection, right? But because you can't be at both places at the same time, you can't be a male and a female at the same time, this probability is 0. So all I really need to do is add those two probabilities, right? So the probability I'm trying to find here, going through a long explanation here, is the probability of diet is going to be it's going to be 60 out of 100 times 0.7 plus 40 out of 100 times 0.6. And if you multiply that out, that turns out to be 66%, which was exactly the same thing that we got when we computed it with the data presented as a table, 66% for the first part. Now, it happens to be more work here, but this probably would be the right strategy if you were given the information in this form. Okay? All right, let's look at another question. We'll move on to B. I'm going to erase part of this and leave the tree because we're going to keep using a tree for each of these strategies here. I'll say for part B, so I'm changing this now to B. For B, we want to find the probability that the student is a female. Okay, now in this case, the tree is actually very easy because in the tree, the first decision is female. So it's really just this part of the tree right here, the probability of taking that branch and stopping, because it's not asking us about the diet at all. So the probability would simply be 60 out of 100 or 0.6. And that also matches the probability we got when we worked this problem with the table. Okay, so that's that. Let me back up here and we'll take a look at C. So for C, let me change colors here a little bit. For C, it's asking us to find the probability that a person prefers diet soda given that they're male. Diet soda given that they're male. So I'm going to use the idea that I'm supposed to have the bottom of the fraction be some either a count or a probability that relates to being male. So how is it that I could be male? Well, if I just go ahead and say I'm going to start right here, I'm just going to say I'm moving right to that point, then I'm saying there's a 100% chance that that can happen. I'm just going to restrict myself to this part of the tree. And that essentially means that I don't even have to think of this as a fraction anymore. I could think of this as being over 1. There's a 100% chance that I'm in the male portion of the tree. Now I want to find the probability that I would like diet. And that probability would just be the 60% right here. So it's just 0.6 over 1 or just 0.60, which is the same thing we got when we did this by hand, using the table. Okay, so another way to think of it is a conditional probability may just be a section of the tree. So I just need to say this probability right here. Another way to think of it, maybe even a better way to think of it, would be to say, this probability right here would be labeled the probability of being a male, and this probability right there would be labeled the probability of liking diet given that we are a male, and that's exactly what we're being asked to find. So it's just that 0.6 directly from the tree. All right, let's move on and take a look at another one. I'm backing up here to erase. Okay, so for part D, it's asking us for the probability of liking, of being a male, given that you like diet soda. Okay, so this I'm gonna, I think, have to use a fraction, and the diet part is going to relate to the bottom of the fraction, right, the denominator. So for that, I'm going to look at all the ways that I can, in fact, let me put this next to it so I can draw that distinction. The bottom, the denominator of the fraction is going to be related to diet, right? So how many ways can I get to diet? I can get to diet here and here. So you can think of there being two paths to diet, right? This path right here, and also this path right here. And we know from the work we did earlier on the part A that that probability would be you could be a female with 60 out of 100 probability, and so multiply by the 70% probability of liking diet given a female, or so we'll add that you could be 40 out of 100. There's 40% chance of being a male, and then there's a 60% chance that if you are a male that you like diet. So I'm representing diet, but I'm not using counts, I'm using probabilities. And that's okay as long as I'm consistent, and I'm going to use probabilities on the top too. So the top, the numerator of the fraction, we're going to stay within that conditional sample space that I've got outlined there in black, but we're going to say, okay, which ones are in the event of being a male? And so that's only this particular path down here. So that one path, which was 40 out of 100 times 0.6, that path is the one that goes through male. So that's a pretty complicated thing, but this sort of problem where we're reversing the condition, it's sometimes called a Bayes formula problem because this construction ends up solving it, right? But if you plug that all in your calculator, it turns out to be 0.3636, the same as we got when we did the table. So that'd be how we would do that problem using the tree. Okay, and then if I back up here and we can look at the last part E. Oops. The last part. Okay. What's going on here? Yeah, let me just erase it from here. Part E. Okay, so part E says we want the probability that somebody is a female and prefers diet soda. Okay, so female and prefers diet soda. So that's actually one particular end node on here, right? They have to be female and they have to like diet soda. So it's just the probability of being there in the tree, right? And so that one would be 60 out of 100. That's the probability of being a female multiplied by the probability of being liking diet given that you're a female, which is 70%. And then when you multiply that out, that turns out to be 0.42, exactly the same as we found with the table. Right, so in this B version of the problem, we had the same information, but it was given kind of as two events, gender and then the percentage of liking diet soda as for gender. So the tree diagram might be the best way to put that information into a form where we can use it to solve, right? If we're lucky, we have it in the form of a table. That's probably the easiest one to use. But if we have percentages, we could construct a tree. Okay, we're going to look at one more on this. I know we're spending a lot of time on this, but this is a good thing to show how many different representations you can do for one problem like this. Okay, another representation of the same information. A sample of male and female students, 100 students total, were asked whether they preferred diet or regular soda. 18 females preferred regular soda. There were 60 females in the sample. 34 students preferred regular soda, and then find those same probabilities. So the way we're going to do this one is using a Venn diagram. Okay, so a Venn diagram is another way to represent this. So I'm going to create separate ones for each version. So for part A, let's just go ahead and make this. Basically, we have people that like regular and diet, and we have females and males. So for each of those variables, I'm going to choose one of the conditions, and I'm going to make a circle for that. So maybe I would say I'm going to have a circle for people that like regular soda. This is going to be a circle for people who like regular soda. And then I'll have another circle that overlaps that for people who are female. Okay, so now if I populate a Venn diagram, we know we should always populate from the inside out. So here it says 18 females prefer regular soda. That means they're in the female circle and they're in the regular circle. So I'm going to put a count there of 18. It also said there were 60 females in the sample. So if I take 60 and I subtract 18 that I already know about, that leaves 42. So there's a space for 42 more females to fit in the other part of the female circle. And then 34 students preferred regular soda. So 34 students, if I take away the 18 that are already in the regular circle, that leaves 16 left. So 16 would be here. And then there's going to be some that are outside of both circles. So if I took all 100 students and subtracted the 16 and the 18 and the 42 that I already know about, that turns out to be 24. So there are 24 students somewhere out there. Okay, so that's how we would populate a Venn diagram. And a Venn diagram is not a bad way to represent things if you have counts, especially if you have kind of overlapping cases, and where you have things like a count of people that are two things, females and preferring regular soda. So how can we use a Venn diagram to answer these same problems? Well, for part A, what we're going to do is, so let me actually pair this. This is going to be our kind of baseline Venn diagram. So for part A, we're finding the probability that a person likes diet soda, right? So that is a simple probability, no conditional probability. So that means it's going to be out of all 100 students. And then we have to include everything that's in the diet circle. Well, there is no diet circle, right? Basically, the regular circle, it's everything outside of that. So you can think of it as everything not inside that black circle. And that would be the 42 plus the 24. So if I just added those up, that turns out to be 66 out of the 100, or 66%. So that, again, matches the probabilities we calculated before, but this time with a Venn diagram. So it'd be everything outside that Venn diagram. Okay, and if I decided to do the second problem using that same Venn diagram, let me back up a little bit here. Okay, so for part B, we're finding the probability that an individual student would be a female. So this is a simple probability. So again, it's out of all 100 students. And this time it would include the people that are inside the female circle. So the female circle's there. Now we're talking about being inside the circle. So it'd be 18 plus 42. Those are the numbers that are inside the circle. And that turns out to be a total of 60 out of the 100. And therefore, that's 60% probability. Okay, again, matching what we had before. Okay, let's take a look at another problem. So if I look at part C, this one is a conditional probability. We want to be the probability that we like diet soda given that we are a male. Okay, so conditional probability means that we're going to have to look at a conditional sample space, not the entire Venn diagram. So males, right? Males are everything outside of this female circle. So I'm going to actually kind of shade it. It's this part out here, right? And so that means that I need to include the 16 and the 24. So 16 and 24 is the total number of students that are males because they're outside of the female circle. And then the diet would be the ones that I just highlighted here that are diet. Well, we have this regular circle, so the 16 here are not diet drinkers. That would be specifically the 24. So it's going to be 24 out of the 16 plus 24. That's 24 out of 40, and that turns out to be 60%, the same as we had the last time we worked this problem in the other forms. Okay, so that's that problem. Okay, let's look at problem D, part D. So for part D, we're finding the probability that a student who prefers diet soda, that's the condition, is a male. So the probability that they're male given that they prefer diet. So in this case, again, it's a conditional probability, so we're not going to talk about the entire sample space. We're only going to talk about the people that are liking diet. So that's going to be everything outside of the regular circle. So all of the area outside of the regular circle, which consists of these two numbers, 42 and 24, right? 42 plus 24. And then in that conditional sample space, how many people are males? So those would be not the 42 that are in the female circle, it would be the 24 that are outside of the female circle. So that would be 24. This time it's 24 out of 66, and that turns out to be 0.3636. So again, just like when we did this with a table or with a tree. Okay, and then for the last one, part E, for part E, we can find the probability that somebody is a female who prefers diet soda. So female and diet. Okay, this is back to being a simple probability, so it's out of the entire Venn diagram of 100 students. Right now, we're specifically looking at only people that are females and like diet. So being in the female circle is female, but this 18 that's in the female circle, they like regular. So it would be just this 42 that are in the female circle, but they're outside of the regular circle. In other words, they like diet. So it would be 42 out of 100, or 0.42, which is, again, the same probability. So we spent a lot of time on that, but it's just to illustrate that there are many different strategies we can use, and it turns out that the strategy we pick might actually be determined by the way we're presented the information. So if you're presented with overlapping counts, a Venn diagram is probably a good strategy. If you're presented with percentages or probabilities, then a tree diagram might be the appropriate approach. And of course, if you're presented with a table, then you would just use the table directly. All right, let's go ahead and move on to another problem. So this one says, what is the probability that one number from the following set of numbers will be even? And then it lists a set in roster listing there. So go ahead and pause the problem and then give this one a try. Okay, so I'm going to go through my strategy list here. What are we talking about? Well, we've got a set of numbers, right? And only these discrete values are allowed. So I don't have a continuous amount of numbers. I just have the discrete numbers listed there, a very specific set of numbers. We're talking about a probability problem. We're talking about the probability that we're selecting one number, so that makes it a single event. And then that means that since it's a single event, it might either be the conditional probability or a simple probability, right? I don't see any condition listed in here, so we're talking about a simple probability, and that means we're talking about equally likely cases and trying to count the event space and count the sample space. Okay, so that's our strategy that we're going to use. That's how we determine the strategy. Here's some things to remember about equally likely cases. When we have equally likely outcomes, the probability of the event happening is the number of outcomes in the event space divided by the number of outcomes in the sample space, or the number of desired outcomes over the total number of outcomes. And then we have all these counting strategies, right? One of them is to list out all the cases and just count them up. So that's the one we're going to use. Since we have a possible set already listed, it's just a matter of counting these up. Okay, so now I think we've got the strategy. We're going to do probability of having an even number. So we're going to use the equally likely cases. The bottom is going to be a count of the sample space, right? And the top is going to be the count of the event space, right? So the sample space is already listed out. And if I count that up, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers in there. So there's 9 possible equally likely choices to make. And then the event space is only the even numbers. So if I made a set for the event, I would go back through here and include only even numbers. The 2, the 6, the 8, the 12, that's it. And so that's 4. And so this problem would just be 4/9, or in decimal form, 4444. Okay? So definitely a single strategy is the appropriate approach there, and it's the simple case of equally likely cases. Okay, let's move on to the next one. This one says we have 2 fair 6-sided dice that are thrown, and the sum of the 2 dice values is computed. What's the probability that the sum will be 10? So go ahead and pause the video and try this problem. Okay, as I look at this, there's a couple ways we could probably go. We definitely are talking about individual sums, and if I have only 6 possibilities on the first dice and 6 possibilities on the second dice, then there's a limited number of possibilities of sums. So that's a discrete situation. They're integer values that are being added to integer values, so we have integer values. We're talking about a probability problem. And actually, there are 2 ways to approach this. We can either talk about the sums themselves, which makes this a single event problem, or we can talk about the individual dice throws, which means we're talking about multiple events. What happens when the first dice is thrown compared to the second dice? Okay, so let's actually solve it both ways. So if I go with the single event approach, then I'm talking about an equally likely outcomes case, because all of the sums, if I list them properly, I can list them in a way that they're equally likely to occur. And we have all of our counting strategies. One of our counting strategies is that you can use tables, tree diagrams, or grids, especially for 2 dice, right? So I'm going to use that approach to try to list out the sums, right? So a good strategy, if we're dealing with this as a single event, is to list, okay, for 1 die, we have the values 1, 2, 3, 4, 5, and 6. And we have 1, 2, 3, 4, 5, and 6 for the other die. And then if I list the sums that happen, if I add those up, if I have a 1 and a 1, the sum is 2. If I have a 1 with a 2, the sum is 3. 1 with 3 is 4. So I can quickly build a table here with all of the sums. This is a way, just a strategy to, one strategy to count things is to list all the possibilities, right? And a grid, a 2-dimensional grid, is a great way to list all the possible sums when you add up 2 dice. Okay, so here's all the possible sums. Okay, and if I just count them up, there's 36 possible sums, right? And they're all equally likely to occur because I've listed every possibility, right? So I've got a probability that I have a sum equal to 10, So all the possible sums would be 36. There's 36 possible sums in that table, right? But how many of those are equal to 10? Well, there's 1, 2, 3, right? So it's going to be 3 out of the 36, right? 3 out of 36, which turns out to be a probability of 0.0833. So this would be probably the way I would do the problem. I would think of the sums themselves as the item I'm concerned with, and therefore it's an equally likely case, a single event. Okay, but that's not the only way we can deal with this. We could think of this as 2 events by considering each dice throw separately. So just to remind us about what we know about that, right? When we have and or together, we already saw this in the first example, that when you have and or, you multiply across to get probabilities, and then you add if you have or cases. So or is add and is multiply in general, right? So what would have to happen here? Maybe I could list, if I'm talking about individual dice throws, I could get a 6 the first time and then a 4 the second time, right? Or I could get a 5 the first time and a 5 the second time, or I could get a 4 the first time and a 6 the second time, because those are really the only ways that I can get a sum of 10. So I could think of each dice roll independently and then say, okay, what's the probability that I would get a 6 the first time? Well, that's 1 out of 6 because they're equally likely cases, and there's 6 possibilities if I have a 6-sided die. Right? If I had a 4, the probability that the second one is a 4 is 1/6, and because it has to be 6 and 6, I'll multiply those probabilities. Same thing for 5 and 5. The probability of getting a 5 is 1 out of 6. The probability of getting a 5 the second time is 1 out of 6, and I'd multiply that. And also for the 4 out of 6, it's 1 out of 6 chance of getting a 4, 1 out of 6 chance of getting a 6 for the second time, and those would be multiplied. And because, so it's basically 6 and 4, 5 and 5, and 4 and 6, and we multiply. So each of these are multiplications. Now, because it can be the first case or the second case or the third case, we're going to add that. Right? So that would be 1 times 1 is 1, 6 times 6 is 36, and then also another 1 36, and also another 1 36. So that gives me 3 out of 36, which is 0.833, the same as when we did it with counting the sums individually. So there's two separate strategies. Just to review, go back there for a second. Right, there's two separate strategies. We can either consider the sums, which means we're talking about a single event, and then we have to list all the sums. Or we can talk about the individual dice throws, and then we can use the and or rules. Okay, both strategies are perfectly good. Okay, let's look at another problem here. This one says, if 2 cards are drawn from a standard deck of 52 cards without replacement, what is the probability that the second card is a jack if the first card is not a jack? Okay, so pause this, give it a try. All right, so here's the situation. I would just model it this way. I would say, it tells me the first card is not a jack, so I'm going to use that symbol X to mean not a jack. And then the second card is a jack, right? First card's something other than a jack, second card is a jack, okay? And I want to find the probability that the second card is a jack given that the first card is not. First is not a jack. That's really what I'm trying to find. It's a conditional probability. So what I'm really after is just this second probability here. What's the probability of that second thing happening? Okay, well, let's see. If the first card was not a jack, right? We started out with 52 cards, right? And if I draw a card out, right? How many of these are jacks, right? If you look at, there's 52 cards. 4 of those are jacks, right? Because there's a jack of clubs, jack of spades, jack of hearts, jack of diamonds. And that means that there are, 48 cards that are not jacks, okay, in the deck. So if we draw a card out and it's not, this one is not a jack, then it means that, that this has dropped to 47, right? And we now have only 51 cards to choose from for the second card, right? What's left in the deck is we have 4 jacks, and we have 47 cards that are not a jack, right? So that means the bottom of this is going to be all the things I could draw a second card. There are 51 cards left to draw from, so that would be a 51 on the bottom. And out of those, if the first one wasn't a jack, all 4 jacks are still in the deck. So that means this would be 4 out of 51. And that probability is 0.0784. So that would be the appropriate way to do that. I really only know that's really the only strategy I can think of for doing that. One important thing is to realize it's only the probability of the second event. It's not really anything to do with the first, and it's not the multiplication of the two. It's asking us about the conditional probability. Okay, let's take another one. So this one says, last month, 186 cars were sold at a large car dealership. 124 had leather seats, 118 had onboard GPS, 99 had Wi-Fi for passengers, 72 cars had leather and Wi-Fi, 70 cars had leather and GPS, 75 cars had GPS and Wi-Fi, 60 cars had all 3 of these options. Find the probability that a car selected at random had Wi-Fi but not leather or GPS, had none of these 3 options. So pause this and then give this one a try. All right, so let's look at our tree here and see if we can figure out strategies based on that. So Sorry, I changed this a little bit. Fine. Okay. So let's see. We definitely have integer values here, right? We have certain numbers of cars. We're not going to ever have 70.57 cars, something like that. So we're not talking about a continuous. We're talking about a discrete thing. And all these are probability problems, so definitely probability, right? But as I look at this, we have a lot of combinations of things going on, right? We have leather option, we have Wi-Fi option, we have GPS. It seems like, and we have things like 60 cars had all three of these options. So that to me is telling me we have multiple events going on. We have multiple events. I know we're drawing a single car, right? But I think I'm going to use strategies where we're combining and or. So what are some things we have here? If we have or cases, we have things like Venn diagrams or the or formula. If we have and cases, we have tree diagrams in the and formula. Um, so let's just try, from experience, I think what's going to work best here is if we use a Venn diagram because we have cars that can have GPS or they can have Wi-Fi or they can have another. So I think we'll try this with a Venn diagram. Let's try it with a Venn diagram. And again, I'm modifying this problem a little bit just to make sure that the numbers work out. Okay, so a reminder about Venn diagrams. We cover that in lesson 7. Venn diagrams are great for word problems that have a lot of information. We always want to make sure and start with the most overlap region and don't forget to subtract what's already been accounted for. So in this case, if I was making a Venn diagram for this, I would have 3 circles for the different options. I'd have a circle for leather, right? I would have a circle for Wi-Fi, and I would have a circle for GPS, and I would make them all overlap because it says that 60 cars had all 3 of the options. So we're going to start by trying to figure out what the number in the middle of this would be, and that's this right here. 60 cars had all 3, so I'm going to populate this Venn diagram with counts. You have to pick either counts or probability and stick with that. So we're going to go with counts here because the data is in terms of counts. All right, so let's take one of these other numbers. Let's take this number here. 72 cars had leather and Wi-Fi. So leather and Wi-Fi would be this area right here, leather and Wi-Fi, the overlap of those, right? And it says that we have to end up having 72 cars in that red area. But we've already accounted for 60 of them. So if I subtract 60 from 72, that means there's only 12 cars left to go in that remaining spot. So this is what's meant by we have to make sure and don't forget to subtract what we already have accounted for. Okay, if I decide to take this number, right, we've got 70 cars that had leather and GPS. Leather and GPS would be this football shape over here. And if we have 70 cars, but we've accounted for 60 of them already, that means there's 10 left to go here. Okay, and then we have 75 cars that have GPS and Wi-Fi, which is this other football-shaped area down here. And of the 75, we've already accounted for 60 of them, right? So that means 75 minus 60, there's 15 cars left to go here. All right. Now, other numbers in the problem. There's 124 cars that have leather seats. So that means everything in the leather circle has to add up to 124. But I've already counted for 60, 70, 82 of those. So if I take 124 and I subtract the 82, there's 42 remaining. That would go right here. 42 left that we haven't accounted for in the leather circle. And if you use that same strategy, right, we're talking about 118 had onboard GPS. That would be this circle. Everything in there has to add up to 118, but we already have 60, 10, and 15. So if you subtract those from 118, that turns out to be 33. Right, 33. Write that a little bit better. 33, okay? And then the last number like that is 99 Wi-Fi. So the circle for Wi-Fi has to contain 99. And we've already counted for 60, 15, and 12 of that. So when you subtract, what's left is 12. Now there's one more area that we haven't yet talked about, and that is the part that's outside all the circles, right? If you add up all the numbers in the circles accounted for already and subtract it from the 186, Some of the cars don't have any of those options. It turns out there's only 2 cars. When we add that all up, all the numbers that are in blue there, it's 184, and when you subtract from 186, there's 2 left to be on the outside. Okay, so now that we have that, then it becomes fairly straightforward to find this probabilities. The probability that a car would have Wi-Fi, right? This is a simple probability, right? So it's going to mean out of all 186 cars, so the entire Venn diagram, how many are in the Wi-Fi bubble? So we could add up all the numbers in the Wi-Fi bubble. So it'd be 12 plus 60 plus 15. All of that out of 186, which I think they told us directly that that added up to 99. That was given in the problem, 99 out of 186. And so that probability would be 5323. All right. And then the second part there asks us, what's the probability that somebody liked Wi-Fi but not leather or GPS? So I could say and not leather. Leather has to be not true, and not GPS. So you could write it like this. So here's a way to think about that. If something is true, Wi-Fi, it means it needs to be inside the Wi-Fi circle. If something's not true, leather is not true, it has to be outside the leather circle and outside the GPS circle. So I'm looking for things that are inside the Wi-Fi circle, but not in the leather circle or the GPS circle. And so that leaves just this 12 right here, that 12. And so this is going to be 12 out of all 186. And that turns out to be 0.0645. Okay? And then the last one asks us for the probability that we have none of the options. And so that would mean out of all 186, that would be the number that's not in any circle, which is this 2. So it would be 2 out of 186, which turns out to be 0.0108. Okay, so a Venn diagram is a really good strategy when we have a large number of quantities and they seem to overlap in various combinations. Okay, let's look at this problem next. This one says we've got some abstract events A and B. We don't know what they represent, but the probability of A is 40%, the probability of B is 30%, and we're told that they're independent. Could we find the probability of A and B, A or B, and ask are they disjoint, why or why not? Find the conditional probabilities A given B and B given A. So go ahead and pause the video and give this one a try. Okay. So there's a couple ways we could proceed here, but since we're talking about and or, we're just going to, I think, since we already have this as abstract values, I would just use the and or formulas. So let's look at the or formula. The way I remember it is if I think about two events, A and B, then I know that the probability of A or B, let's actually do this first. Right, the probability of A or B, let's do and first. Sorry, I was getting ahead of myself there. So we need the and formula first. This is a symbol for and. So the way I think of that is, if I think of a tree, like A and then B, part of a tree here, then this would be the probability of A, this would be the probability of B given that A happened, and this out here would be the probability that A and B happened. Right, so I use that as a little mnemonic to remember that the probability formula for A and B is the probability of A times the probability of B given A. Right, so I would use that formula. Okay, but they also told me here that A and B are independent events. So the definition of independent events is that the probability of B doesn't depend on A, and that means that the probability of B given A is the same as the probability of B given that A doesn't happen. It's just the probability of B period. So that means the probability of B given A can be written just the probability of B. And so I could write a simpler version of the and formula, the probability of A times the probability of B. And therefore, since we're given those probabilities, 0.4 and 0.3, we can just multiply those to find the answer. And that turns out to be 0.12. So that probability would be 0.12. Okay, let's take a look at part B. So part B says we're going to find the probability of or. Okay, so for part B, I'm going to use my mnemonic for remembering or formula, which is Venn diagrams. If I have A and then a B circle, the probability of A or B occurring is the probability of A plus the probability of B, but we have to subtract off any overlap, right, so that it doesn't get counted twice. All right, so now I know that the probability of A is 0.4. I know the probability of B is 0.7, but we just found out in the last section in part A that the probability of the AND is 0.12. So I could just now plug that value in with the rest of the OR formula, and that turns out to be 0.58. So the OR formula. Okay, part C, it asks whether or not A and B are disjoint. Are they mutually exclusive? Okay, so just a quick review of that, right? Mutually exclusive means that there's no overlap at all, right? Another way of saying that is the probability of A and B would have to be 0 if it was mutually exclusive. But in part A, we calculated that the probability of A and B was actually 0.12. And that means this is not true, right? It means that there has to be an overlap here because there is a 12% chance of being in the overlap region. So because of that, this is no. The answer to this is no. They're not mutually exclusive. And the reason for that is because the probability of A and B is something other than 0. So I would use that as the reason. The probability of A and B is 0. Or you could just say because there's overlap. All right. Okay, let's look at D and E. These are conditional probabilities. So for D, we're trying to find the probability of A given B, right? And so, you know what, maybe I could, I need some way to represent B and A within B. Because I just did an OR thing there, I think maybe a good strategy would be to use the Venn diagram. That'll help me picture this a little bit. We know that the probability of A and B is 12. We know that the probability of A is 0.4, but we've accounted for 0.12 of it already. That means if I took 0.4 and subtracted 0.12, I would have 0.28 left. I know that the probability of B is 30%. 12% is accounted for already, so that would leave 18%. And if I add all of that up, that turns out, and subtracted that from 100%, there's 42% left over that would be outside of A and B. So there's a completely populated Venn diagram with probabilities. So now I could find these conditional probabilities. The probability of A given B. Well, B represents being in the B circle, right? So the B circle would be 0.12 plus 0.18. Those are the total probabilities of being in B. And then the portion of that that's in A is just the overlap part, the 0.12. That's in B, but it's also in A, right? Now, if you prefer to do the conditional probability thing instead of the Venn diagram to find this, right, this ends up, another way to think of this, if you don't like the Venn diagram approach, is you can start by doing this. If I'm saying the probability of A given B, you can say, okay, let's put B first as an event and then A, and then label these probabilities. This is the probability of B. This would be the probability of A given B. And this out here would be the probability of A and B. And if you did the multiplication, that's probability of A and B is equal to the probability of B times the probability of A given B. And then if I solve that for this, I could divide both sides by probability of B, and I will get what's called the conditional probability formula. The probability of A given B turns out to be equal to the probability of A and B divided by the probability of B, right? So this 0.12 is really the probability of A and B. So we could plug the 0.12 in directly from part A, and then the probability of B is 0.4, which is the same thing we're going to get when I compute it the way I did with the Venn diagram. So it's 0.12 over 0.4, whether you decide to do it from Venn diagram or from the conditional probability formula. And that turns out, therefore, to be 0.4. Okay? If I wanted to do the same thing with the other probability, the other conditional probability for part E, it's asking us for the probability of B given A. If I wanted to do that with Venn diagram, I could say, let's first find the probability in A, which is 0.28 plus 0.12, and then I'll take the portion of that that's in B, which is the overlap. So it's going to be 0.12 divided by 0.3, right? Wait, 2, that's 0.4, right? Did I do the wrong thing here? Oh, I made a mistake on this one up here. Sorry. This number, actually, this number is 0.3. Sorry, let me back up. Probability of B is 0.3, and if I add 0.12 and 0.18, that's 0.3. Yeah, that's actually the right number because this one is the one that adds up to 0.4. 0.12 over 0.4 turns out to be 0.3. Or you could use the conditional probability formula. The probability of B given A is going to be the probability of A and B given or divided by the probability of A. And so it would be the 0.12 divided by the 0.4 to get the 0.3. All right, so Venn diagram or conditional probability formula are both good strategies for the last two parts there. Okay, moving on here. Now we're covering a lot of problems with a lot of different kind of strategies here, but we'll keep talking here. It says a person is dealt 4 cards from a standard deck of 52 cards. What's the probability that they're all clubs, all diamonds, or all hearts? I didn't do this on the last one, but let's go ahead and look at the chart again to see if this will help us. Well, we're talking about numbers of cards, right? So we can't have like fractional numbers of cards. We either have like 1 card, 2 card, 3 card. So I think we're still talking about condition or discrete here. We're talking about a probability problem, right? And well, all clubs, all diamonds, or all hearts. I think that's pretty clearly to me an or situation. So that means we're talking about multiple events, specifically or, and so the things that work for or are Venn diagrams or the or formula, where if there's no overlap, we can use the simplified disjoint formula. So I think we're either going to do or Venn diagram or formula, and I think maybe this one might be best if we just went with the or formula, right? So and or, basically the rules are that we multiply if we have and we add for or. That's kind of what this is stating here. So let's actually solve the problem that way. If I state it this way, what would I have to have? I'd have to have a club, 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 and or I could have diamond, 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 or I could have heart, 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 right? Okay, and actually, I should be even more specific than that. I should write it like this. I should write club and club and club and club, or all of that, or diamond and diamond and diamond and diamond, right? So there's an implication that there's an and in between each of these, right? It just gets too long to write it this way. So if I write C, 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 then what I mean to say is club and club and club and club. All right, so what's the probability that the first card would be a club? Okay, well, there are 52 cards in the deck. A quarter of them are clubs, which is 13. So that'd be 13 out of 52. Okay, now, and the next one would have to be a club. So let me show you something here. If I'm talking just about these first two, probability of a club, the first one being a club and the second one being a club, that's going to be the probability that the first one's a club times the probability that the second one is a club given that the first one is a club. Remember, the and has to have the second would be a conditional probability. So the probability of the first one being a club is 13 out of 52. But the second time, we've already had a club drawn, so that means there's 51 cards left, and of those, 12 of them are now clubs, right? So the second one is a conditional probability. 12 out of the remaining 51 cards are clubs. And this third one is also conditional. This is going to be the probability of getting a club again, given that the first two were clubs, and the probability of getting another one that's a club, given that the other 3 were clubs. So we were going to drop that by 1 each time. Okay, now when we get to an or, right, an or is a completely different expression of the way to get the event to happen. So it's like we start fresh. We have a fresh deck. When we cross over an or boundary here, that means we're going to add, but we're starting fresh. A fresh deck. We have 13 out of 52 cards are diamonds. If I take one of them out, there's 51 cards. 12 left are diamonds. 11 of the remaining 50 are diamonds, 10 of the remaining 49 are diamonds. That would be this right here. Or, so I'll add another case, again with a fresh deck. So I have 13 out of 52 times 12 out of 51 times 11 out of 10 times 10 out of 49. And those are really identical, so you could almost think of it as just 3 times this number. So if you entered it all in a calculator, you could do 13 divided by 52 times 12 divided by 51 times 11 divided by 10 times 10 divided by 49, and then just multiply that by 3. And that turns out to be 0.0079. So I think this one pretty clearly going to be an and or rule problem. We have 3 different ways to meet the criteria, all clubs or all diamonds or all hearts. But to evaluate one of those, all clubs, it's a club and a club and a club and a club. So remember, you multiply for and, you add for or, and every time you start over with or, you start fresh. The problem starts fresh. Okay, let's take a look at this problem. So it says that a shipment of 20 televisions, 6 are known to be defective. If 10 televisions are selected at random from the shipment, then what's the probability that 3 are defective? What's the probability that all 10 are defective? So pause this and give this a try. All right, as I look at this, well, let's look and consider our options here with the choice. Again, we have counts of things, right? So we're still not into anything with continuous probability. This is discrete. It is a probability problem. And what do we have here? I think we have, well, as a couple questions here, right? We can talk about, I think, even though it seems like we have different things, right? We have some are defective, some are not, right? We're really kind of drawing a sample from the shipment. 10 are selected at random, so I think I'm going to consider this a single event. In other words, I don't really see that there's an or situation here, like this can happen or this can happen to meet the criteria, right? It is true that in some ways it's like an and, right? We have to have one defective and another defective and another defective. But I think I can evaluate the entire, in other words, if you think of drawing 10 TVs at random from the 20, that's a single selection. And all the different ways I could do that are all equally likely to occur. So that, if I think of the whole selection as a single event, I could use single event, right? And that means this is just going to be calculating a simple probability, which is equally likely cases, right? There's no particular reason that any group of 10 is more or less likely to be selected than any other group of 10. So I think we're going to use equally likely cases for this one. And for that one, we just have to count the number of outcomes in the event space that we meet this criteria that 3 are defective or 10 are defective out of the total number of strategies there for the sample space. So we're going to have some counting strategies. What I see, if I kind of make a picture here, is, I have this on a separate paper? No. Yeah, okay. So what I really see is we have 20 TVs, right? And we have 6 of them that are bad, they're defective. That means we have 14 good TVs, right? And if we're drawing a sample of 10, so we're going to draw 10 of the TVs in the sample, right? We have to have 3 of those be defective for this first problem, right? So 3 have to be bad, and that means that we would have 7 that are good. So what that looks like to me is that we're drawing 3 bad TVs out of the 6 bad ones and 7 good TVs out of the 14 good ones, right? So let's look at these strategies for counting. We could list out all the cases. Well, that's going to be really hard because there's many, many, many thousands of ways that could happen. So I don't want to do that. We have multiplication principle. We have choices, right? And in a way, this is going to be that because I have to select some bad TVs and some good TVs. Do I have a permutation or a combination? That's where I have a set of distinct objects without repeats, and I'm selecting things. It's kind of like a combination, right? Because I'm selecting TVs, and once I select them, I can't select that same TV again. But I think it's strategy 5 here that we're going to use, multiplication principle with combinations. So this is if I have multiple choices to make, but each is a choice of a number of items out of a set. That's what's going on here. I have to choose some bad TVs, I have to choose some good TVs, and each of them come out of a set of good TVs and bad TVs. So we're going to use that principle there. Okay, let's review the problem again then. So for part A, I'm finding the probability that we have 3 defective TVs. Okay, so if I picture the situation this way, like I said over there, 20 TVs, right, and we have 6 are bad. I'm going to use that for defective. There's 14, therefore, that are good. And I have to make a selection. I'm going to choose 10 TVs, right, and out of those, for this to be true in the event, then this is 3 have to be bad, and we have to therefore have 7 that are good, right? 7 that are good. All right, so the way I'm going to count this is if I disregard the 3 defective rule and just say I'm going to select the 10 TVs, right? This selection here, 10 out of 20, that defines the sample space, right? The sample space is going to be the number of ways to select the 10 TVs. Okay, so since I'm selecting them out of a set, and they're used up when I select one, that's a combination or a permutation. I'm going to call it a combination because it's just going to end up in my sample. I don't care if it's the first TV I selected or the 4th TV, it just ends up in my sample. So I have 20 TVs, and I'm selecting 10 of them where the order doesn't matter. So that would be 20, choose 10, or 184,756 ways to get 10 TVs selected out of 20. Okay, now when I'm talking about the event space, that's going to be the number of ways to select specifically 3 bad ones, and therefore also 7 good ones. All right, so that means I have 2 choices to make now. I have to select the bad TVs, and I have to select the good TVs. Right, so these are also going to be combinations, but this time the bad ones, we're going to select 3 bad ones, but they have to come from the 6 bad ones. I can't select bad ones out of the good pile, right? And I have to select 7 good TVs out of the 14 good ones, and I'm going to multiply those 2 things. I'm going to multiply those 2 things here. All right. Okay, so we are selecting we're selecting the bad TVs, we're selecting the good TVs, and because we have to make the bad TV selection and the good TV selection, we have to multiply those. So the multiplication principle, right? So that turns out to be 20 times 3,432, which turns out to be, well, I don't have that number calculated. Let's go ahead then and put this into the probability statement. So this probability, right, the sample space number is 184,756 different ways to select the TVs without regard to whether they're good or bad. And then in the numerator, we're going to have 20 ways to select the 3 bad ones out of 6, and then times 3,432 ways to select the 7 good TVs out of the 14 good ones. And if you plug that in a calculator, that turns out to be 0.3715. Okay, so the first one, definitely this is an equally likely cases one. I think that's probably the best strategy to go with. So for part B, let me just do this down here. Part B, that's the probability that all 10 are defective. So if I use the same strategy, let me kind of draw a picture again. We have 20 TVs. We have 6 bad ones. We therefore have 14 good ones. And we need this time to draw a selection of 10, and all 10 of them have to be bad, 10 bad, and therefore no good ones. Okay, so what we're doing is we're selecting 10 bad ones out of 6 bad ones. Okay, actually, I can see a problem right there. It's impossible to get 10 bad TVs if I have to select them out of 6 bad TVs. So without any further calculation, I can state that the probability of getting 10 bad TVs in the sample is 0. And that's because there's only 6 bad TVs in the sample. So there's no way that we can get all 10 of them to be bad. Okay, let's see. Let's see if we can do a couple more here. So this one says two events, E and F, occur with the following probabilities. E is 30% probability, F is 60%, and that should say E and F. The probability of E or F is 70%. Okay, are events E and F mutually exclusive? So pause the video, give this one a try. Okay, let's look at strategies. We have these probabilities. Yeah, we don't really know exactly. I don't know if I would really say continuous. Well, let's look at continuous for a second. Continuous probabilities has to do with things like probability density functions or normal curves, things like that. I don't see anything in this problem that leads me to believe that. These are not integer fractions, right? But these aren't the data values. These are the probabilities. So I think we're still over here in discrete probability space. We have probabilities. We definitely have multiple events here because we have an event E and event F, right? So, and we're looking at an OR situation here. That's just the symbol union for OR. So we're talking about OR. And so strategies for that are Venn diagrams or the OR formula. So we could use either one. I think in this case, maybe, well, let's see. Yeah, we could use the OR formula, which is written here, or we could use the Venn diagram, right? And we're talking about disjoint, which is another word for mutually exclusive events. So what is it that we know about that? Well, events are considered mutually exclusive or disjoint if there's no overlap or if the probability of A and B is 0. Right? So really, whether or not these events are mutually exclusive depends on whether or not the probability of the two events of event A and B is 0. Right? So what we're really finding here is we want to figure out, we need to know what is the probability of E and F. Because if that probability is 0, then that means there's no overlap, and therefore these are disjoint or mutually exclusive. Right? So one way that we could calculate this, I think, is to use this formula. This is probably the best way to do it. Let's use the formula. I'll write it for E and F. So we have the probability of E or F. That's equal to the probability of E plus the probability of F minus the probability of E and F. And in the problem, they gave us a number of these probabilities. They told me the probability of E is 0.3. They told me the probability of F is 0.6. And we're trying to figure out what the probability of E and F is. And they told me the probability of E or F is 0.7, so that would go out there. So what I have here is 0.7 equals 0.9 minus probability of E and F. And I can algebraically solve for this. It turns out that the probability of E and F has to be 0.9 minus 0.7, or 0.2. And since that is not equal to 0, it means that it's this case right here. The two events are overlapping because this probability, there is a probability here. It's something other than 0. So we could say that E and F are not mutually exclusive or not disjoint. We'll use mutually exclusive because that's what they said. So not mutually exclusive because there is an overlap. Okay, I think we're going to stop there for this video. We've gone on for more than an hour here, and we'll pick up in the next video and cover some additional problems.